Alrighty, y'all. Today we're taking a look at homework 3 for Physics 211, and we're going to jump right into it with our sneak peek questions. Alright, so our first one, we have a few equations. Alright, we have our a minus b is 3, b minus c minus 1 is 7, c minus 2 is 4. And we're trying to solve for a, b, and c. Well, right off the bat, I have 3 equations and 3 unknowns, so it should be a solvable system. And I'm actually going to start with this one, this equation over here, because it has the least number of unknowns. It doesn't have a and b or c and something else. All right, it just has c. So if I add 2 to both sides, I'll get that c is 6. Then I can use that in this one, because this one just has c and one other unknown. And I can plug in that c is 6, and if I add 6 and 1 to both sides of my equation, I'll get that b is 14. And then again, I can plug in my 14 for b, and adding 14 to both sides, I'll get that a is 17. All right, so it's this kind of like cascading series of systems of equations that we'll see in the rest of these problems. Our next sneak peek question says that suppose a bicyclist is riding their bike on a flat road. Regardless of what they do with their pedals and brakes, they stay on the road. What must be true about their acceleration vector? And we're not calculating anything. So this is saying that whatever they do with their pedals and brakes, they're staying on the road. What that means is they're not jumping up off of the road. And I'm going to draw myself a little bike here. Right, with pedals and stuff. They're not jumping up off the road, and they're not sinking into the road. They're just moving along it. So if I were to say with my axes looking like this, the x direction and a y direction, that means that the only acceleration that they'll have is in the x direction. So we can say that the y component of their acceleration will be 0, right? They're not going to be accelerating at all in the y direction. They're just accelerating in the x. And now our bicyclist is riding down a hill, sloped at 10 degrees. Again, regardless of what they do, their pedals and brakes, they stay on the road. What must be true about their acceleration vector? Well, same thing that we said as before. I can take this entire thing and just tilt it at 10 degrees. Right? They're riding on a hill, so it doesn't say if they're going up or down. Doesn't matter. But again, they're not jumping up off of the hill at all. Right? So their acceleration vector, before we said, oh, the y component will be 0. But now the same thing is true, that their acceleration will be directed along the slope. So if I say that these are my axes like this, and we've been calling these my parallel component and my perpendicular component, I draw little arrows on my parallel lines. It still just means parallel. But if I have my parallel and my perpendicular components, I know that my perpendicular component of acceleration will be 0, because the acceleration is just directed along parallel to the slope. Okay. So with that, we're going to get right on ahead to our main questions. All right. So the first one, we have a person with a mass of 60 kilograms standing in an elevator, and we're drawing a force diagram for a few different situations. So I'm standing in an elevator, and when I'm drawing my force diagrams, I think about what is physically touching the person. Well, if I draw a little picture off to the side, here's my elevator, here's the person, the floor is touching the person. So, what direction is the floor pushing on the person? Well, it's pushing up on the person's feet. So I can call that the force of the elevator, or since it's a person standing on a surface, I can call that my normal force. The force that is normal or perpendicular to the surface that the person is standing on. Normal means perpendicular. We do not put a normal force on our diagram unless we can say this force is perpendicular to this surface. All right? So then we are also on Earth, so I'm going to add gravity in as well. Right? And there is our force diagram. Now, the fun part about this is that I didn't even consider what the elevator was doing. So my force diagram will look pretty much like this for all three situations. Because no matter what the elevator is doing, right, my normal force isn't going to change directions. The floor is not going to pull down on my feet. It's only ever going to push upwards. So the only thing that'll change is the relative magnitudes of my normal force and my force of gravity. But we'll look at those when we set up our Newton's second law and solve for some numbers. But in general, this is what our force diagrams are going to look like. So the first one is when the elevator is at rest. So I can tell myself off to the side that my acceleration will be 0. Reminder that I do not put accelerations on my force diagram anywhere. All right? So if I set up my sum of my forces, saying my sum of my forces, and if I'm thinking about adding these together, well, the one step that I skipped, I didn't say which way was positive. I'm going to say that up is positive for this one. All right? So I have my normal force, which is acting in the positive direction. It's acting upwards. So I take my normal force, keep it positive, and I'm going to add my force of gravity. But since my force of gravity is going downwards, and I said up was positive, that means I'm going to add a negative force of gravity. Or if I just want to cut out the complexity of that, then I just subtract. So now I have added up my forces. Reminder that sigma F is an instruction for what to do with your forces. I'm not doing any math with this term here at all. It just tells me add up my forces, and I did. And that's going to equal my mass times my acceleration. But we just said that the elevator is at rest, and it is staying at rest, so my acceleration is 0. So I can say that will equal 0. So rewriting that real quick, Fn minus Fg equals 0. And now this is the equation that I'm going to be doing some math with. All right. So we're trying to find the magnitude of each of the forces. Well, I know that for the force of gravity, that's going to be my mass times little g. So I can do that. I'll do that up here actually, right? Fg will equal m times g. So that'll be my 60 kilograms times my 10 meters per second squared. And that will be 600 newtons, right? So if I come down here then, doing some algebra, I'm going to add my force of gravity to the other side of my equation. So I'll get that my normal force is equal to my force of gravity in this case. So that means that my normal force is also going to be 600 newtons. So I'll put that up here. Right. So now I just have to move on to my next case, which is my elevator accelerating upwards at 5 meters per second squared. So just as a reminder, I'm going to put that off to the side. Again, my acceleration is upwards. But again, not on my force diagram. For my force diagram, it is what is physically touching the object, and also if we're on Earth, we add gravity to it. And again, I'm just going to say that up is positive to keep things consistent. So if I'm setting up my sum of my forces, I'll have, again, a positive Fn and a negative Fg. And the mass of the person hasn't changed, and little g hasn't changed. So that's still going to be my 600 newtons. But now when I set up my Newton's second law, I've added up all of my forces, and when I set it equal to my mass times my acceleration, now I have to think about having an acceleration term. So my elevator's accelerating upwards at 5 meters per second squared. I said up is positive, so that means my acceleration, well, I can also include my mass, my 60 kilograms, and my acceleration, 5 meters per second squared. Right? So I already know what my force of gravity is, or the weight of the object. So I'm just solving for my normal force. So my normal force, that's going to be 60 times 5. That'll be 300. And I add my force of gravity over to the other side, my 600. So I'll give you my normal force will be 900 newtons. Okay. And just a reminder that my little g here, that's not a negative number. The only reason that I have a negative sign in front of that force is because I said when I was adding up my forces that this force is going downwards. I said that down was negative, so I accounted for it right here. So when I plug in g, I'm plugging in a positive number because g on its own is a positive number, and then we can assign a sign to it depending on how we are setting our axes. Okay. So our last case that we're going to move right along to is my elevator is accelerating downwards at 5 meters per second squared. So if I do that, I'm going to write my little acceleration off to the side, again, just to remind me what direction it's going, and just keeping things consistent. I'm going to say that up is positive again. So when I set up my sum of my forces, it's going to look just the same as it did before. My normal force in the positive direction and my force of gravity in the negative direction equals my mass times my acceleration. But this time, I was going to plug in that mass, 60 kilograms. When I plug in my acceleration, now my acceleration is going downwards, and I said that down was negative, so I'm going to be plugging in negative 5 meters per second squared instead of the positive. And again, putting all this together, I'm solving for my normal force, because again, I know my force of gravity hasn't changed. My normal force, well, that's going to be now minus 300 plus that force of gravity, 600. So my normal force is just going to be 300 newtons. Okay. So I've set up Newton's second law, and I've solved for all of my forces. You will also notice that I did not solve for any net force, right? I did not say, oh, the acceleration is causing a force. We considered that by saying that this force is going up and this force is going down, and together they will cause an effect. They will cause an acceleration. But if we're asked to solve for the forces, I can't just take that acceleration, multiply by a mass, and call that done. We have to think about what individual forces are acting on the object. And in turn with that, our next problem, or less of a problem, but more of a discussion, is to go visit an elevator somewhere on campus and ride up and down. When it's accelerating upward, what do we feel? When it's accelerating downwards, how do we feel? And then based on those observations, are there connections that we can draw with the forces in our force diagram? Well, for this, we have our correspondent in the field ready to show us a little bit of a demonstration. So take it away, Sydney. Thanks, Sydney. So now we have our scale and we have our object that we're going to put on the scale. All right? And we can see that normally it's 9.65 ounces, but if I start accelerating upwards, if the elevator is going to start going, there we go, we can see that the scale starts measuring much higher. All right? So it measured up to a little over 10 ounces on that one. And the elevator's doors are going to open, but we're going to just go right back down. And now as I'm accelerating downwards, the scale will read a much lighter normal force, closer to 8 ounces. And then when we get to the bottom, we're still going downwards, but as we slow down, we're going to be accelerating upwards, so we can see that force is going to increase again. Right? But the weight of the object, the weight of the physical object hasn't changed. The mass hasn't changed, so the force of gravity hasn't changed. The scale's just reading the force that it needs to exert in order to hold up the object. It's reading the normal force. Back to you, Sydney. Thanks, Sydney. From that demonstration, we could see that my little Lego telescope was heavier. The scale thought that it was heavier while I was accelerating upwards. So I can say that accelerating up made the scale think the object was heavier. And accelerating down, that's when it thought the object was lighter. Right? So there's our connection to that. So if we go up to our previous force diagrams, when I was accelerating upwards, my normal force was a lot higher than it was in my previous situation when I was at rest. And when I was accelerating downwards, my normal force was a lot lighter than it was when I'm at rest. So all this to say, when I'm feeling heavy or light in an elevator or in any kind of accelerating box, it's because really what I'm feeling is the normal force or the force of the floor pushing up on my feet either a lot more or a lot less. So whenever I see apparent weight, right, I should immediately be thinking about my normal force. All right. Moving right along, we have a 2,000 kilogram car driving at 20 meters per second, and the driver wants to stop over a distance of 30 meters, and we want to find the force that the brakes must apply to the car in order to do this. And we're assuming no air resistance. So we're solving for a force. The first thing I want to do is draw a force diagram. So in terms of, well, actually the first thing I should do is draw a picture. So here's my car. I'm not very good at drawing cars. It's going that way. This is a terrible car. It's all right. My car is going that way, and it's driving on the road, and it wants to stop over a distance of 30 meters. And just to keep things consistent, I'm going to say over here is where my 0 is, and I'm going to say 30 is over here, which tells me that this way is positive. Okay. So if I'm drawing my force diagram, all right, I'm going to think, what is touching this object? Well, the road is touching the object, and the road is a surface. So it's going to be pushing up on the car with that normal force. And also, the other part about the road is that that's what the brakes will use to slow down. So I'll have friction slowing me down, pulling the car backwards. All right, so I'll call that the force from the brakes. And then we're also on Earth, so we have to include gravity in there. mg. Right. Now, in this problem, I'm trying to solve for the force of the brakes. And just looking at it, it doesn't look like this normal force is going to give me any new information. Right? I know my force of gravity, but if I solve for my normal force, if I set up my sum of my forces in the y, it's not going to give me any new information. So I think our more important one to set up in this case would be sum of the forces in our x direction. And in that case, I said to the right was positive, so I have a negative force of the brakes as my only force acting in the x direction. And that should equal m times my acceleration in the x direction. If I wanted to set up my sum of my forces in the y, just saying up is positive, it would just give me Fn minus mg, or my force of gravity, equals may. But we talked again before about how our acceleration in the y for a thing just going down a road is going to be 0. So that just equals 0. Again, doesn't give me any kind of useful information in this case because I don't really care what the normal force is. I could solve for it if I wanted to, but we don't really care what it is. It's not going to help us figure out the force of the brakes. Well, if I want to figure out the force in the brakes, then I know the mass of the car. The only thing I would need is the acceleration in the x direction. And there's a way that we have talked about solving for the acceleration in the past, and that's with kinematics. So our acceleration is kind of our go-between between kinetics, which is why things move, and kinematics, which is just describing how things move. So if I say my x t equals x naught plus v naught x t plus 1/2 ax t squared, and I'm also going to write our v of t, vx of t, will be v naught x plus ax t, and our third and final kinematic equation is our v final x squared minus v naught x squared equals 2 ax x final minus x. Right? So I have my 3 kinematic equations just in the x direction over here, because again, the car's not moving at all in the y, so we don't really care about it. But when I'm talking about this, typically we've said for kinematics, I know the acceleration, or I'm solving for the acceleration, but I don't really care why I have that acceleration. I just know I am accelerating, and this is what will happen to the position because of it. And this is what will happen to the velocity because of it. Over here, I'm saying, okay, I have a bunch of forces acting on my object, and because of that, it will cause the object to accelerate. So that's kind of my translation between, again, kinetics and kinematics. So based off of my kinematics, I'm going to try to figure out my acceleration in the x direction so I can then use it in my kinetics. So we're going to write down all of our potential variables, my v final x, v naught x, my x final, my x initial, my acceleration in the x, and my time. And we get to figure out which of these do we know and which of these do we not know. Well, I know that the car is driving at 20 meters per second to start. That's going to be my initial velocity. And then I know that the driver wants to come to a stop, which means that my final velocity is 0 meters per second. I also know that I set my initial position of the car at 0. I just said that was a thing that was true. But I also know that we want to stop over a distance of 30 meters, which means my final position, where I have that final velocity, will be at 30 meters. And again, my acceleration, that's what I'm trying to solve for. And I don't really have any information about the time. I don't really want to solve for it, so that one's probably not going to be super helpful. And all of this, because I have all of this information, well, I have all of this information and I'm solving for this, and I don't really care about time, I'm going to get rid of the equations that involve time, because then I'll have to solve for time first and then plug into a second equation. And this one I can just use directly. So, I'm just going to move my variables off to the side. I'm going to plug my things in. I have my final velocity is 0. My initial velocity was 20 meters per second. My acceleration, that's what we're solving for. My final position was 30 meters and my initial position was 0 meters. So solving this around for AX, I'll get minus 400 over 2 times 30 will be 60. And that will equal acceleration in the x. You'll also notice that my acceleration I solved for and got a negative number. Coming back to my picture, that makes sense. If I'm moving, my initial velocity is positive, I'll need a negative acceleration to slow it down. And we already said before that my acceleration is being caused by a force going in the negative direction. So again, it makes sense that my acceleration is coming out to be negative. So if I take that and plug it in over here, we get that again, minus my force of the brakes is MAX, and AX, we just said, was minus 400 over 60 units. I forgot my units. That was my bad. That's going to be in meters per second squared. Okay. So if I rewrite this real quick, minus my force of the brakes will be minus 400 m over 60. I just moved the mass up into the fraction because it's multiplying, it's all the same. And because it's negative on both sides, I'm going to multiply both sides of my equation by -1, so I can just get rid of that. Because remember, FB, that's the magnitude of the force of the brakes. I have already accounted for the fact that it's going in the negative direction. So when I get a positive solution for the magnitude, it should make sense. So if I just plug in the mass of the car, then I will get my answer. So plugging in my 2,000 kilograms, that's going to give me a force of 13,333.33 newtons. roughly. Right? So this connection between forces and kinematics is something that will be very useful, because I can figure out what forces are acting on an object, then I can describe its motion based off of my calculated acceleration, or I can calculate an acceleration and figure out what force I would need to apply in order to make that happen. Moving right along again, we have our locomotive with a mass 4m pulling a train consisting of 2 other cars. Each of the cars has a mass m, but the locomotive has a mass 4m. The first thing I want to do is draw a picture of that before I do anything else. So fortunately, I have my train picture ready to go with my masses all labeled on each of the cars. And each of the cars is experiencing a backward force of friction in the wheels, and the locomotive is attached to the first car is attached to the second car. And we want the cars to accelerate forward with an acceleration alpha. So I'll draw that in my cartoon. That's an alpha. It's a Greek letter. Fancy. All right. And we're calculating forces that the cars apply to each other and making sure that the couples in between, or the little bits that hold the cars together, that's not going to break. And we also need to calculate that the traction force that the locomotive must apply in order to accelerate all of the cars. So how much force does the driving car need to use to drive for all of these cars to go? So we're drawing a cartoon of the situation, labeling anything interesting, choosing a clear set of variables for the various things, and we're going to need some algebraic symbols for all of the forces and all that. So if I'm in labeling important things, I'm going to label my x direction and my y direction. And then saying that these are my positive. And then in terms of algebraic variables, we're going to be using a lot of subscripts. I'm going to call my locomotive L. And my first car, that's going to be car A. And my second car will be car B. All right, so I've set myself up pretty nicely to be able to denote the forces between all the different cars. So the next step, while we draw our cartoon, I'm going to draw my 3 separate force diagrams, one for the locomotive and one for each car. So I'm going to start with the car in the back. So I just think that one might be the easiest, because the only thing that's going on is the only thing that's touching the car, well, is the ground. So I'll have some normal force of the ground pushing up on it, but also the other car. And the car A is going to be pulling it forward. So I'll call that force of car A on car B. And we use what we call dealer-feeler notation, where the first object listed is the object that is dealing or exerting the force on the second object. The second object is the feeler, the object that is feeling the force. So A exerts the force, and B is the car that is feeling the force. So we have our normal force from the ground, because the ground is touching the car. We have the force of car A pulling car B forward. And we also were told that we'll have a friction force. That's going to be going backwards, because we're saying the cars are going forward. And then because we are on Earth, we also get to include gravity. Right. Moving on to our second car. I'll put that one here. This is car A now. Again, I have the ground pushing up. And I'm still on Earth, so I'll still have my force of gravity. All right. And a reminder, my force of gravity is my mass times a little g. And I use m because that's the mass of my car in this case. Eventually we'll have to do force of gravity with 4m. That's the only difference. All right. And we had A pulling B forward. So now if I'm thinking about car A, I have B pulling A backwards. And we also have that friction force that we were told that we had in our problem statement. But also, if I think about what else is touching car A, I also have the locomotive pulling as well. So this will be the force of the locomotive on A. Then, lastly, I have my locomotive. Again, I have my normal force from the ground. I have my force of gravity, but in this case, again, like I said, my mass is 4 times m. So I have to do 4 times m, that's my mass, times little g. I'm trying to figure out the force that's being used to drive the train forward. I'm going to call that force driving, all right, or you can call it traction, whatever we want. And we also have car A pulling back on the locomotive. And that is all of our force diagrams. You'll notice there's nothing of car B pulling on the locomotive. That's because car B isn't touching the locomotive. What I like to think about when I'm drawing my force diagrams is I draw a physical circle around the object that I care about, and anything that passes through that circle, in this case the ground isn't drawn, but anything that passes through that circle becomes a force. So I can see that the ground breaks the circle, and this coupling here, or A pulling on this coupling here, also breaks the circle. Same thing with my locomotive. I only have A pulling back on the locomotive. B is not touching my locomotive at all. So now we're going to set up our Newton's second law for our 3 drawn force diagrams. We're set up in the x and the y direction. I already set that up and right are positive, so we're going to go with that. So starting again with car B, so I'll call this some of the forces on B in the x direction. And in our x direction, I have FAB acting positive, FAB acting in the positive direction, and I have FF acting in the negative direction. And that's going to equal the mass of the object, which is just m, times our acceleration, which in this case, our acceleration in the x direction is going to be that alpha, because the whole car is going to be accelerating at that alpha, or the whole train, I should say. Now I can do the same thing, sum of my forces on B in the y direction. And in the y direction, I have my normal force from the ground minus mg from the weight, and that's going to equal my mass times my acceleration in the y. But again, since the train is only accelerating along the track, it's not going to be accelerating in the y direction, so I can just say that's going to equal 0. On to my next car, and it looks like I'm running a little bit out of space. I'm going to be crowded together. So I can set up my sum of my forces on car A in the x direction. Again, in the x direction, I have FLA acting in the positive, FLA. And acting in the negative x, I have FF and FBA, minus FF minus FBA. And that's all I have acting in my x direction. So again, that's going to be m times my acceleration in the x, which is that alpha. Now I sum up all my forces in the y direction. Again, I have my normal force positive minus my mg is negative, and again, we're not accelerating in the y, so that's going to equal 0. Last but not least, we have our locomotive. I sum of my forces on the locomotive in the x direction. Acting positive, I have my force of driving. And acting in the negative direction, I have my force of A on L. So force AL. And again, that's going to equal my mass times my acceleration, except the mass of the locomotive is not m, it's 4 times m, but it has that same acceleration, the same alpha. Again, I do my sum of my forces on the locomotive in the y direction. That'll give me my normal force minus my 4mg for my weight of the locomotive, or the force of gravity. That's going to equal 0 as well. Now, also what I should mention that I should be, that's not A, that's B, should be denoting that these normal forces are going to be different, or even if we don't know that they're going to be different, we don't know for sure that they're going to be the same. If I solve for them and they're the same, excellent. But if not, then we want to make sure that we can account for that. So we say that they're different to start. If they end up being the same, we can state that later on. But now I have Newton's second law all set up. And now I have to count my unknowns. We can see that our y equations aren't going to be super helpful because we're trying to solve for a lot of the forces in the x directions. So it's really just good practice setting up that y direction. But really we're going to be using the x equations more so. So in terms of things that I don't know, I know that I was given m, I was given alpha. I was also given ff. So those are all known values, but I wasn't given FAB. That's something that I'm solving for. That's one of the forces in the couples. I come over here. Again, I wasn't given FLA. That's one of the forces in the couples joining the carts together. But I was given my force of friction. I wasn't given FBA, but I was given the mass and the acceleration. Lastly, I was not given the force driving. That's something I'm solving for. Wasn't given FAL, but I was given 4m and alpha. So counting these all up, I have 1, 2, 3, 4, 5 unknowns in my 3 equations. And unfortunately, that means I can't really solve that without more information. Right? I need at least as many equations as I have unknowns in order to solve it. So what we can do is we use Newton's third law, which says that the force of A on B, the magnitude of that force, which we denote just by not putting the arrow over the top, this has the same magnitude as force of B on A. But if I were drawing them in vector form, they have the same magnitude, but they go in opposite directions. Right? Since we've already accounted for the direction of all of these forces, right, I drew AB going to the right on B, but I drew BA going to the left on A. I've accounted for the fact that they're in opposite directions, so I can just say that their magnitudes are equal, and it makes my life a lot easier. So what I'm going to do first is I'm just going to solve this equation over here because, like we talked about before with the sneak peek questions, this one only has one unknown, so I can just solve directly for it. So I'll get that FAB is M alpha plus FF. And then, like we said, FAB is the same as FBA, so I can take this and plug it in over here for my FBA. So I'll have FLA minus FF minus, said it was M alpha plus FF equals M alpha. And in this case, again, just reminding us, I know everything in this equation besides FLA, so that's the one I'm going to solve for. FLA, that's going to be my M alpha plus FF plus M alpha plus FF, because this one was from here. And I can combine all my like terms. I have 2 M alphas and I have 2 FFs. So that'll give me that FLA. It's going to be 2 M alpha plus 2 FF. Right. And now I can take this and plug it in over here, because FLA and FAL are a Newton's third law pair as well. And I can rewrite this, jumping all over the place. I can say FD minus FAL, we said was 2M alpha plus 2FF, and that will equal 4M times alpha. Again, the only thing I don't know is that FD, so solving for my driving force, it's going to be 4M alpha plus 2M alpha, so 6M alpha plus 2FF. And that will give me my driving force of the locomotive. So I have successfully solved for my forces in the couples and the driving force of the locomotive just in terms of M, alpha, and FF. moving right along. Now we have our sled sitting in the snow. And we have 3 people pulling on it. We have the first rope pointed at an angle 45 degrees north of east with a given force, another rope that is due south with a given force, and a third rope pulling 30 degrees north of west with a given force. And we want to stop the sled from moving. In which direction should we pull? So, first thing I'm going to do is draw my force diagram. So the first rope was 45 degrees north of east. So that means here's east. I want to go 45 degrees north of it. So that tells me here's my first one. There's my 45 degrees. And that one was 200. I'm going to call that F1. That's going to be 200 newtons. My second one was pointed due south, which is just straight south. And that one was, we'll call it F2. That was 300 newtons. And I have my third rope that was 30 degrees north of west, which means here is west, and I'm going to go 30 degrees north of it. So here's my 30 degrees. And that one was, call it F3. That one had a force of 100 newtons. And we're trying to stop the sled from moving, which means we have to apply a force in some direction. Now, I don't know what direction that is, but it could have an X component and it could have a Y component. So I'm just going to draw those in. I'm going to say that this is my fourth force. This is just the Y component of it. And this is also part of that fourth force. That's the X component of it. So clearly we have some vectors that aren't aligned with our axes. So we're going to have to break those into components, just like I have that force 4. Technically, it could be going any direction and have any magnitude, but I'm going to solve for the components first, because then I can use those to figure out the magnitude and direction of the original force. You'll also notice that I assumed them going in the positive direction. I like to do this because then what happens is if I do all my math, I assumed positive in the beginning. If I do all of my math and the number that I get turns out to be negative, that means it's going in the negative direction. But if I guess that the force is going negative and then I do all my math and get a negative answer, it means I have to flip my direction like I did before. This time a negative answer would mean going in the positive direction because I would have to be flipping from negative. So I just like to do it like this. Really what it means is if I get a negative sign in my answer, it means flip the direction that I thought I was going. But either way, I have to break things into components, and that's going to be our next step. So I'm going to start with force 1, put that down here. And force 1 was 200 newtons. F1 equals 200 newtons at an angle 45 degrees. So in this case, drawing our triangle like this. This will be my F1x. This will be my F1y. I'm going to throw a trig function at it. I'm going to say sine of 45 degrees is opposite. So opposite to this angle is F1y over my hypotenuse is F1. So I can solve this and say that F1y equals F1 sine 45. Then I'll throw another trig function at it. We'll say cosine. And cosine will be my adjacent side. So my F1x over my hypotenuse. And then again, I can solve this for F1x. Oh, that says sine again. My bad. Should still say cosine 45. Right. And then I also have to break F3 into components. F2 is already aligned. So the x component of that would be 0, and it's just in the y direction. So F3 I can do the same thing. I'm going to draw it this way. F3 was 100 newtons, and it was at an angle 30 degrees right there. So when I'm drawing my triangle, which these lines don't look very straight, but when I'm drawing my triangle, this is going to be my F3x and my F3y. So if I throw my trig function at it, I say sine of 30 is opposite over hypotenuse. So it'll be F3y over F3. And cosine of 30 will be F3x over F3. Again, I can solve these for my F3y and my F3x. So doing all of this, because sine and cosine are both root 2 over 2, I'll end up with F1y being 100 times root 2 newtons. F1x is also going to be 100 over root 2 newtons. Because this is a 45, 45, 90, means this is an isosceles triangle, and my F1x and y should be the same, so that answer makes sense. Then I'm getting my F3y and my F3x. My F3y, that's going to end up being 50 newtons, and my F3x is going to be 50 times root 3 newtons. The only other thing that I haven't said yet is that I haven't considered any of my signs on my components just yet. I'm going to do that once I put them up on my second force diagram. I always like to draw two force diagrams, one that shows me where the forces are acting and the other one that shows me what direction their components are going in. So if I were to do this, I would have my F1x going to the right, because if I'm looking at F1, it's going to the right and up. So I have F1x going to the right, and I have F1y going up. Then I have F2 going straight down. So I have that, F2. Then I have F3 going left and up. So I'll have F3x and F3y going to the left and up, respectively. And then lastly, my guesses as to what my applied force is. So my F4x and my F4y. All right. You might also notice that I'm stacking my arrows on my force diagram. This is just how I like to draw my force diagrams. Really, all of these arrows are acting, all of these forces are acting on the same point. They're acting at the same point. But I just like to stack them because that's how we add vectors that are aligned together like this. And I like to visually see that, okay, these two are going positive. I'm adding those together. This one's going negative. These three are going positive. That's just how I like to do that. But now what I'm going to do is I'm going to set up Newton's second law. I'm going to set up my sum of my forces in the x direction. And the forces I have acting in the x direction, well, I have F1x and F4x acting positive and F3x acting negative. So I have F1x plus F4x minus F3x. And again, I want the sled to not be moving, so I'm going to say that equals 0. I can also set up my sum of my forces in the y, and that's going to be, well, I have 1, 3, and 4 acting positive and 2 acting negative. So F1y plus F3y plus F4y minus F2. And that will also equal 0. Again, we don't want the sled to be moving. So if I solve this real quick for F4x, because remember we have the other two, we're just trying to solve for F4x. I'll add f3x to the other side and subtract f1x. And what that's going to give me, it's going to end up giving me minus 54.819 newtons. And then again, I can solve this for F4y. My F4y will be 108.58 newtons. All right. So like I said before, I had guessed that my applied force would be acting positive in the x direction, but I just got a negative number, which tells me it was actually supposed to be in the negative direction, negative x direction the whole time. So I can say that's going to be 54.8 newtons that way. It's also, but it's going positive up. That's what we got from our 108.6 newtons that way. So our total applied force will be going left and up on our original sled. So now all we need is the magnitude and direction. And if I have two components of a vector, we've talked before about how to get the magnitude and the direction of our vector. So I draw my angle theta in this corner down here because that's how I chose to set up my triangle. So I'm going to say that tangent of theta is going to be opposite over adjacent, so 108.6 over 54.8. And I take my inverse tangent, and that's going to give me that theta equals 63.2 degrees. And I can label it on my diagram very clearly, but I'm also just going to say that that's north of west. All right, from west, I'm swinging in the northern direction. And just lastly, I'm getting my magnitude. So it's going to be my 54.8 squared plus my 108.6 squared, all square rooted. And that's going to give me a magnitude of 121.63 newtons. So putting it together, 121.63 newtons at an angle of 63.2 degrees north of west. That'll be my final answer for this one. On we go. We have a 1 kilogram book sitting on a frictionless table in outer space, but someone is pushing on the book with a force of 9.8 newtons diagonally downward. So just drawing that picture. Here's the book resting on a frictionless table, and the force at that angle, the angle is to the vertical in this case. So I'm pushing down and to the right. So if I were to be drawing my force diagram, I think what is physically touching my object? What is physically touching the book? Well, we know that there's a force that's being applied down and to the right on the book, and that's at an angle of 30 degrees to the vertical. And, well, the only other thing touching our book is the table, and that's a surface, so we're going to call that a normal force. All right, normal to what? Normal to the surface. I'm just going to call that the force that's applied. And normally, I finish out these force diagrams by saying, well, we're on Earth, so we also have gravity. But now, we're not on Earth, we're in outer space, so we don't have a force from gravity in this case. So now, the first thing I do when I'm given vectors that aren't aligned with my coordinate axes is I break them into components. So this applied force at my angle of 30 degrees here will have my y component and my x component. So I'll call that FA, which equals 9.8 newtons. And this will be my FAX, and this will be my FAY. And in this case, all right, my angle is here, so sine my FAX will be FA sine of 30, and my FAY will be FA cosine 30. So I have it all broken into components, and I'm just going to draw myself another little force diagram to show the components. So I have my FAY going down, I have my FAX going to the right, and I have my normal force going straight up. And now I'm going to write my Newton's second law. So I'm going to say my sum of my forces in the x direction. Well, the only thing I have acting in the x direction is that FAX. We said that was FA times sine 30. So sine of 30 is going to be 1/2. So I'm going to call that FA over 2, which again is just my FAX. That equals my MAX. Then I'll have my sum of my forces in the y. And that will be, well, my normal force in the positive direction. So I'm saying up is positive. And my FAY in the negative direction. My FAY is just FA times cosine of 30. So that's going to be in the negative direction, FA, and then cosine of 30 is root 3 over 2. I just like to keep things in terms of radicals and fractions. It makes more sense to me, but if you want to punch that into a calculator, you are more than welcome to. But again, my sum of my forces in my y direction will be MAY. And now we need to talk about what they mean, what all these pieces mean in words, right? So we said that this is FAX, which is the component of the applied force in the direction that is parallel to the surface. Right? I said that this is my x and y. The direction that's parallel to the surface is my FAX. This is the component of my acceleration that is parallel with that surface. Same thing over here. My normal force, that's the force from the surface that is perpendicular to that surface. By definition, normal means perpendicular. But this is the component of my applied force that is also perpendicular to the surface. And again, this is the component of my acceleration that is perpendicular to the surface. Because we're not moving through the table at all, my acceleration in the y direction is just going to be 0. Which will give me that my Fn minus Fa root 3 over 2 equals 0. So if I'm trying to solve for the magnitude of the normal force, and my book isn't moving through the table and it's not jumping up off the table, I can get that my normal force will be Fa times root 3 over 2, and Fa was just 9.8, so that's going to come out to about 8.487 newtons. And if I'm solving for my acceleration, over here, we said this component of my acceleration was 0. This one is the one we're going to be solving for. So again, solving for A, I can divide my mass over to the other side. The mass of the book was just 1 kilogram, so that'll be Fa over 2m equals Ax. Again, plugging in my 9.8 newtons for Fa and my 1 kilogram for my mass. That'll give me an acceleration of about 4.9 meters per second squared. Okay. Not too bad, just the same procedure we've been doing. Draw your force diagram, break things into components, figure out what's going in what direction, Newton's second law, algebra. It's going to be the same procedure when we go on to this version. All right. So now we're back on Earth and we have gravity again. But now we have that same 1 kilogram book resting on a slope that is inclined at an angle of 30 degrees. So now here's my book on the slope. So when I draw my force diagram off to the side, I like to sketch in the slope. This isn't a force, it's just a dotted line to remind me where the slope is. Because when I think about what is physically touching my object, it is just the slope. So I'll have a normal force or a force that is perpendicular to that slope. And now I have a slope drawn on my diagram, so I can draw my normal force perpendicular to that line. And there's nothing else touching my book, so I'm not going to put any other forces on there, except we're back on Earth. And because we're on Earth, we have gravity again. And gravity is just going to be going straight down. All right, so it's going to be m times g. Now, in this case, we have to think about what we're breaking into components. Because normally it would look like, oh, here are my x and y coordinates. My normal force is the one that's not aligned with it. And so that's the one I'm going to be breaking into components. But in this case, it's actually going to be a lot easier to think about the parallel components and the perpendicular components to the surface. Because we want to align our axes with the direction that we're going to be accelerating. Since we're not going to be accelerating into or out of the surface at all, if I can set up my coordinates so one of them is going in that direction, then I can say my acceleration in that direction is 0, and I don't have to worry about any trig or anything like that. So all I'm saying is I'm going to take gravity, and that's going to be the vector that I'm breaking into components. So I want my perpendicular component and my parallel component, like that, my right triangle. And it's very important that when I'm breaking something into components, that gravity, mg here, is the hypotenuse of the triangle that I draw. So one leg is aligned with my perpendicular side, and the other leg is parallel with my parallel side. And the only thing left is to figure out where my angle theta is. All right, so we were given that this was 30 degrees. So if I kind of envision a right triangle here, this angle is going to be 90 minus that, because all of my angles in that triangle have to add to 180. So 30 plus 90 is 120. So what remains is my 60 degrees here. So this angle will be 60 degrees, but this also makes a right angle. Well, if this and this have to add to 90, well, this is going to be 60. That means this has to be 30. This angle is going to be that same as our theta, our 30 degrees. So all that, just envisioning some triangles, all that to say that our 30 degrees that we labeled for our slope here is this angle of our triangle. So when I come over and I say my mg in the parallel direction, which again is this direction, that's going to be opposite to my theta. I'm going to say that that's going to be mg sine theta. And my perpendicular component is adjacent, so my mg perpendicular is mg cos theta. Again, this theta is actually 30 degrees, so we can get some values for that. It tells me this is going to be mg times root 3 over 2, and this one's going to be mg over 2. Now, you might notice that this is very similar to the previous problem. And in fact, it is the same, because this mg here, right, if I take the mass of the book, which is 1 kilogram, and I multiply by my 9.8 meters per second squared, that is g, that gives me my 9.8 newtons that was being applied as a force before. The only difference is that my force diagrams look a little tilted to what they were over here. But if I were to just copy this and rotate it, it looks exactly the same as our previous problem. So all we did really was tilt our frame of reference into parallel and perpendicular instead of x and y, and it makes things a lot easier. So as I like to do, I'm going to redraw my force diagram just with my vector components so I can keep track of what's going on. So I have my mg perpendicular, which was my mg over 2. I have my normal force, which again is still perpendicular to that surface. And I also have my mg parallel, which was mg root 3 over 2. Right. So now when I'm setting up my Newton's second law, instead of saying x and y, I can think about parallel and perpendicular. Because again, we're just considering the components of the forces parallel and perpendicular to the surface. So in my parallel direction, I just have my mg root 3 over 2 equals my ma parallel. And in my perpendicular direction, I'll have my Fn minus mg over 2, which equals my ma perpendicular. And my ma perpendicular, again, I'm not accelerating into or out of the slope, so my perpendicular acceleration will be 0. And again, like we said, this is a very similar, not very similar, this is the same setup that we had for the previous problem. The component of that gravity force, or that external force, that is parallel to the surface. The component of the gravity force that is perpendicular to the surface. So if I were solving for my normal force, I'm going to get the same answer that I did before. I'm going to get my 8.487 newtons. And when I solve for my acceleration, I'm going to get exactly what I did before. I'm going to get my 4.9 meters per second squared. Because this is how we tackle these types of problems. We just think about tilting our frame of reference as if we were in outer space and gravity is being applied at an angle. All right. Well, I hope you found this video at least a little bit helpful. Let me know if you have any more questions about this or anything else that you want me to try to explain, and I will do my best to try to explain it because I guess Sydney explains stuff.